We're going to sort of continue where we left off last week by taking the next step. So last week we talked about model-free prediction, and this week we're basically going to extend the methods we used to find the value function for MDPs, and we're going to extend those methods into control methods. In other words, we're now looking to solve MDPs. We're looking to find the optimal value function and thereby find the optimal policy for those MDPs. So the way we're going to do things today is we're going to break things up into something called on-policy and off-policy learning. We'll start off with on-policy learning, which is in some sense is the simpler case. This is the straightforward case where the algorithm is following a policy and is trying to learn about that policy. And we're going to start off by extending the methods we had last week, which were Monte Carlo prediction. We're going to extend that to Monte Carlo control. We're going to take the temporal difference learning methods from last week and we're going to extend those to control methods as well. And then we're going to move on to off-policy learning. Off-policy is essentially now where you try and learn about a different policy whilst following one other policy. So that's sort of the agenda for today, what we're going to move through. So to make this a bit more concrete, so last time we're still working in this model-free setting. So everything we're going to talk about today, we're going to make no assumptions that the MDP is given to us. We're going to start assuming that we have an unknown MDP. The agent's just thrown into this world. It doesn't see the dynamics, it doesn't see the reward function. All it gets to experience the trajectories in this world. It gets to pick actions, follow some trajectories, and kind of figure out what's the best way to control, trial and error learning, essentially. So last lecture we did the prediction case, where the policy was fixed. And the idea was to estimate the value function given that policy of that unknown MDP. And this lecture, we're going to turn this into control methods. And the way we're going to do that is we're going to optimize that value function, find the best value function for any policy that you might follow in that MDP. Okay, so why might this be interesting to you? Well, I hope that everyone can find something from this list that they think, oh, that would be a worthwhile thing to do. So these are all examples where what's been done, these are examples where actually these model-free control methods that we're going to talk about today have been applied successfully to all of these examples. So well-known examples of this might be controlling an elevator, parallel parking a car, trying to steer a ship, taking some bioreactor and trying to control it optimally, controlling a helicopter, taking some aeroplane and working out the logistics of that aeroplane, trying to play the game of RoboCop soccer to make your team of robots score as many goals as possible, making an agent to play Quake, managing a portfolio for your financial application, folding up proteins so as to find the optimal configuration, making a robot walk, or playing the game of Go. And what's interesting about these problems is that if you take any one of these, and I asked you the question, what's the MDP? That's a very hard question to answer. We don't know what the MDP is for most of these. These are real-world, complicated problems. You know, if I give you, I don't know, if we take one of these, like a bioreactor, and said to you, you know, what actually is the MDP for a bioreactor, or for a helicopter, or for making a robot walk? I mean, the world's a complicated place, and just working out the dynamics of what happens when a robot, you know, what happens, so its actions might be to increase the torque to one of its motors. And you want to know, well, what effect will that have in terms of the world, in terms of the observations it's going to see next, what's its next sensors going to be at the next time step? These are hard questions to answer, and typically what's done in many cases is you have to either come up with an approximate model of the MDP, which is very likely to be wrong, or what's potentially more advantageous is to actually assume that to use these model-free methods, where you don't make any assumptions about the MDP, and you figure it all out directly from experience. And this avoids making modeling errors. So if you don't know the MDP, then rather than coming up with an inaccurate model of that MDP, we just sample experience directly and directly try and compute the value function and find the optimal policy. And in many other cases, in this, even if the MDP is known, it's often too big to use, except by sampling it in any case. So an example of this might be something like, let's say, RoboCop soccer. Let's say we're actually doing the simulation league in RoboCop soccer. Now the simulation league, there's a simulator. In other words, there's sort of, in some sense, the simulator knows exactly what the dynamics are because someone's had to program this in, and someone's had to say, well, if you take this step, you'll be in this next state. But at the same time, the state space is just too big to try and solve this MDP directly. The branching factor is too large, the state space is too big. And so the only effective way to do this is actually to treat it as model-free anyway, to sample from these dynamics and actually take samples just as if you didn't know what the MDP was. In fact, that's what was successful in the go work to get another large state space. Okay, so that's just some motivation for why we might care about model-free control. So, I mentioned very briefly on and off policy learning, so we'll do more detail in the second part of this class about off-policy learning, but just to give you some flavour, what do these terms really mean, just to give you some intuition. So on-policy learning is kind of like learning on the job. So you're following some policy pie, and you're trying to learn about that policy pie whilst you're sampling that policy pie. So you're following policy pie, and you want to say, well, while I'm following this policy, how good is it to follow this policy? So this is the natural thing in some sense, that you're learning about what you're doing. In contrast, off-policy learning we could think of as sort of looking over someone's shoulder. You're watching someone else behave. They're behaving in some particular way, and whilst they're behaving in some particular way, you want to find out for yourself, well, how should I behave? How well would I do if I was to do something else? It's like, aha, they were behaving this way, but maybe I should actually behave in this other way. So you can sort of watch the mistakes that they make and figure out your own policy from someone else's experience. So this is sort of looking over someone's shoulder. So specifically, you get samples from some policy mu, as we call this in behavior policy, and you want to learn about the target policy pie. Okay, so we're going to start with on policy. So this is learning on the job, the simple case. So we just want to step back to a slide from a previous lecture. So this is when we were talking about dynamic programming. Hopefully you remember this idea of generalized policy iteration. The general idea was this sort of cycle that we start off by coming up with some, we start with some policy, we start with some initial value function. What we do is that at each step we estimate v pi. These today, let's see if I can use this. There we go. So we estimate this v pi by looking at our current policy and using some policy evaluation method to estimate our v pi. So we start off with our pi and we come up with some v pi. And now, given that value function, we can act greedily by greedy policy improvement would be one example, but in general we can use any policy improvement strategy to say, okay, well given our value function we want to come up with a better policy. And now, given that better policy, we're going to evaluate that policy. And given that new value function, we're going to act greedily and come up with a better policy, and so on and so forth until we showed before that in the case of these specific algorithms that for when we're actually acting greedily and using something like iterative policy evaluation, we can show that this really converged on the optimal value function and the optimal policy. And we have this cycle like this, just round and round and round, better policies, better value functions. And so it's natural to ask the question, well, if we want to do control, can we use this same idea in a model-free way as well? Can we just plug in something else as our policy evaluation method here, and perhaps plug in something else here if we need to? And so that's the strategy we're going to follow in this class, at least in the first half. And so to begin with, let's make a guess. Let's say our first guess might be, okay, well we want to do something like Monte Carlo. Our task now is to do something like Monte Carlo control. We want to use our Monte Carlo methods to turn them into a control method. So last time we had this very simple method for estimating the value function, which we called Monte Carlo policy evaluation. This was basically just measuring the mean, if you remember. It's like looking at the average outcome of all trajectories that pass through a particular state and saying that's the value function. And so we have this very simple policy evaluation method. We just run some trajectories, get the mean outcomes, and now we've got an estimate of v pi if we run for long enough. And so we could run that as our policy evaluation, and we could, say, use greedy policy improvement as our policy improvement strategy. Now this might seem like a reasonable idea. Can anyone see any problems? It's actually a hard question, so yeah.
But to do the greedy policy improvement, you need to know the value of the policy when you make a change. So if you change your policy slightly, if estimate the value to get right, so it's quite a lot for us. If you don't know the value of all the little changes you can make.
So I think you've got the right idea. It's not so much that you don't know the policy, because you do know the policy, it's that you don't know the dynamics of the
yeah, as you don't know, so if you change your policy by one step, you don't know what the value of, you have to re-estimate the value of that new policy, right?
Okay, and that's sort of happening here in a sense anyway. So we're changing the policy at every step, and we're finding a better policy and a better policy. And all you need to know to follow this cycle is you need to know the value of your current policy. And so this greedy step is the thing that says if you just change it by one step, what would happen. You evaluate that, and that gives you a new policy. You see what I mean? Sorry, go on.
You just end up in the local minimum and, you know, voluntary.
So amazingly, you might think so, it's natural to think so, but amazingly it turns out that what we showed last in the dynamic programming lecture, and I did have some when I very briefly mentioned this idea of the contraction mapping theory at the end, and amazingly what we showed is that this whole process has a unique optimum. So actually, even though it feels like we're doing something very greedy and sort of myopic, it's actually guaranteed to find, at least in the previous case, it was guaranteed to find the optimal strategy. So let me suggest what might be wrong with this approach. So there's actually something wrong with both of these. So we're going to need to change both of these slightly, but the basic idea is going to be the same. But the first problem is that we want to be model free. And what we're using here is we were using Monte Carlo policy evaluation using V, using the state value function. And the problem is that what happens if we want to do greedy policy improvement and we've only got V? How do we do it? Well, if you want to improve the policy and you're only given V, then you need to look one step ahead. You basically need to say, okay, well, my greedy policy is going to be the policy which chooses the action that has like the best one-step look ahead. So we want to know which action is the best. And to know which action is the best, we have to sort of consider how much reward you might get from taking that action, plus where that might take you to, and what the value is of the state you would end up in. We've only got V. We don't have anything telling us the value of A without kind of doing this computation. And if we're trying to be model free, well, we don't know this. We don't know the reward of the MVP. We don't know the transition structure of the MVP. We don't have these things. So we can't do this. We can't evaluate. We can't directly evaluate how good an action is without doing this sort of one-step look ahead. Our state value function just tells us the value of states. It doesn't tell us directly the value of actions without doing some look ahead. But if we had Q, well, that's what Q is for. This is the state action value function, which we talked about before. But the whole point of Q is that it gives us this thing without knowing the dynamics. So if we had Q, if we'd actually figured out the value of taking action A from state S, then gradient policy improvement would be easy. We would just look at the Q values and we would pick the action that has the highest Q value. That's what greedy would mean if we had the Q values. And so the first thing we need to do is to say, okay, well, if we want to be model free and we want to use the same idea of generalized policy iteration, we need to work with Q rather than with V. Is that clear to everyone? Otherwise, you need to come up with some kind of model here, and we're trying to be model free. You can always estimate the model, by the way, but that's a different class of methods. Those are model-based, which we'll talk about in the subsequent lecture. Okay, so now we've got this idea. But instead of working with V, we're going to work with Q. We're going to apply the same idea. So we're going to start with an action value function and a policy. And then at each step, what we're going to do is we're going to evaluate our current policy by just using Monte Carlo again. So this is basically now our action value function is going to be estimated by the mean outcome of all of the episodes that started in state S and take in particular action A. We're going to get all those means. We're going to come up with some action value function. And then it's easy to act greedily with that action value function. We come up with a new policy that just maximizes our A's over that action value function. And then we're going to evaluate that new policy, come up with some new Q values, act greedily with respect to those Qs, which is trivial again, and keep going. And we're hoping that this is going to give us the optimal solution to the problem. So we've done one of the two steps. The problem is that actually there's still a problem here, and that's the greedy policy improvement, which still isn't quite right. And to get some intuition into that, I'm going to give you a little example of what goes wrong when you use greedy policy improvement in this setting. Okay, imagine you've got two doors in front of you. And this is what happens when you're just some agent and you're following this greedy strategy. And so to begin with, you don't have any information, so you just pick something. So you open the left door and you get reward 0. Okay? So now we're going to estimate, I'm using V here, but we could just, this should actually be Qs, sorry, these are for actions. So imagine these are Qs. So the value of taking the left action, we've seen one reward, so clearly we think that our best estimate of the value there is 0, the value of that action. So now we're going to try the right door. And the right door, we open it and we happen to get a reward of +1. So now we think the right-hand door is the best, right? We've got an estimate of +1 for that one. So we open the right door again. Now this time we get and we get a reward of +3, so our estimate of the value of that right door is +2, just the mean of 1 and 3, we're using Monte Carlo evaluation. So we open the right door again, and we get a reward of, say, +2, and now we think the mean is +2. So we open the right door again, and we open the right door again, and we open the right door again, and so forth. And we never open that left door ever again. Now, it might just turn out we were unlucky, that the very first time we opened that left door, we were just unlucky, and we got 0. And it might turn out that we actually, if we persevered with the left-hand door, it might have actually had a higher mean. So the problem with this greedy action selection is you can actually get stuck. If you stop exploring, you can actually get stuck on a suboptimal action. So greedy action selection, when you're actually running on policy and you're actually using this policy to generate the trajectories of experience, can lead to suboptimal solutions. You need to continue exploring all actions from all states to make sure that you really do find the best solution ultimately. Is that clear? Okay. So the simplest way we can do that is just randomly picking some doors in this example. You want to make sure that you continue to explore everything. So here's a very simple idea. We call it epsilon greedy. And the idea is that we continue to try all actions with some non-zero probability, but we still prefer the best action. So the idea is with probability 1 minus epsilon, we're going to choose the greedy action. And with probability epsilon, we're going to choose an action completely at random. Okay? So, if epsilon is 0.1, that's basically saying 0.1 of the time we're going to just roll a dice and pick an action according to what our dice says. And 0.9 of the time we're going to follow our greedy action and choose the maximum here. So this is just summing together those two parts. And n is the number of actions in this case. So I'm not going to labour the theory, I don't think, but I really want to just stress that this idea actually works. So the main piece of theory we're going to use is this idea that, following on from what we saw in the dynamic programming lecture, if you remember there, we basically wanted to show that when you follow this strategy, that you're actually making progress by acting greedily. We wanted to show that if you start off with some policy and you act greedily with respect to the value function that you have corresponding to that policy. So if you evaluate a policy and then you act greedily with respect to that policy, we want to show that from here to here you've made some progress, that the policy you have here is better than the policy you had here, or greater than or equal to the policy you had here, and this one's better than what you had here, and so forth. And we had a proof in the dynamic programming lecture that that's actually true, that every single step you're making progress, and if you stop making progress, then you've actually reached the optimal policy. And so what we really want to do is just extend that to the idea of epsilon greedy and show that we're still making progress when you use epsilon greedy. And that's all this theorem here is saying. Basically, this is quite informal. This is just saying that what we had before in the dynamic programming lecture was something that said that if we could show that the greedy policy, in other words, you started to say S, you pick your next action according to your greedy strategy, and then you follow what you had before. We basically showed that if this is greater than the value of the policy you started with, we had something called the policy improvement theorem that showed that we really are making progress, that we really are enjoying this. And basically all we're showing here is that that's still true for epsilon greedy policy improvement. In other words, even though we're not acting greedily and we're choosing some random actions, that our epsilon greedy policy after one iteration is going to be better than the epsilon greedy policy we had before. So this is just breaking it up into the parts that we have of picking either with epsilon, picking the greedy action, or with with epsilon choosing a random action, which is this component, with 1 minus epsilon choosing the greedy component. And then you just collect terms together and you can show that this is better than just because we're maximizing over this term here. This ends up being greater than this value here. I don't want to label the theory, I just really want to give you this idea that if you start from here and you step to here, that you really have made progress. And because you're making progress, you're guaranteed to be stepping further and further towards the optimal policy. The question is whether you actually get to the optimal policy or not. So we've got this new strategy now, so we're improving this bit by bit. So we've kind of come up with this is our sort of proposed algorithm now, that we're going to evaluate the policy by Monte Carlo policy evaluation. So we're going to estimate our Q by just taking the mean of all these states and actions. And that's going to take us to these Q pi values. And then we're going to improve the policy by epsilon greedy policy improvement. And we're going to iterate in this fashion until hopefully we get somewhere useful. Now, there's a couple of things that we need to think about here. So, are we ever going to reach all the way to the optimal policy? Well, if we're continuing to take random actions, then by definition we can't be optimal. So if we can keep improving and keep improving and keep improving, but if we don't reduce epsilon down to 0, then we're still taking some random actions. And so if we're taking random actions, we could do better than taking random actions. And so we haven't yet found the optimal policy. So what we'll see in a minute is that you sort of need to decay epsilon in a particular way to guarantee that you really do converge on the optimal policy. But that turns out to be fairly straightforward. So one more point, which is, just like in the dynamic programming case, we had this idea of modified policy iteration. We had this idea that you didn't need to go all the way to the, you didn't need to spend lots and lots of iterations to exactly work out the true value function for your policy at every step. We had this idea that maybe you could just do 1 or 2 or 3 iterations of iterative policy evaluation, make some progress towards this, and then improve your policy. Make some progress and then improve your policy. And we could do the same thing with Monte Carlo control. And in Monte Carlo control, it's particularly natural because now we have something which is actually running episodes. And so the idea is the following. The idea is that we've got some agent, it's going to sort of run a trajectory, gather some experience, and at the end of that episode, it's going to improve its estimate of the value function. So it runs just one episode, and it says, okay, well, I've seen one episode, so even though I've only seen one episode, I can come up with a better estimate of Q than I had before. So it just updates its means from that one episode of experience. So we don't wait until we've seen all of our states and actions infinitely many times. We just update our Qs from that one episode of experience. And then we can immediately improve our policy based on what we've seen so far. So the idea is that just step by step, we make our estimates of Q better, and we always use the latest information that we've had to improve our policy. So it looks a little bit like this. We start off with some Q value, and we're going to just act greedily with respect to that Q value. We're going to run one episode of experience. From that episode of experience, we're going to update our means of all the states and actions that we visited in that episode a little bit. So that means we've now got a new policy where we just act greedily with respect to those new values, run another episode, update our means, run another episode, update our means, and so forth, making progress towards the optimal value and the optimal policy. So we don't need to wait until we've seen everything before we can update our Qs. And this strategy still makes sense. Okay, so this is just the technical requirements to make sure that we really reach this point here. And they're really straightforward. So it turns out that all you need to ensure is that you continue to explore all states and actions forever. You need to guarantee that you will visit all states and actions infinitely many times if you carry on forever. And that should be clear that you need to do that, because if you have a random world, it might be that you've just been unlucky so far and happen to have seen, just like in the door example, you were just unlucky and you happen to see, 100 bad examples of one of the doors, and on the 101st you might have seen that it actually takes you to heaven. So you always need to continue to explore infinitely many times, but you also need to make sure that your policy, in the limit, becomes greedy. So you need to make sure that in the limit you stop taking these random actions, and that your policy will converge on something that's completely deterministic, that just picks the best action all the time according to their value function. So these might seem slightly contradictory, in that we're saying you have to keep on exploring forever, but you also have to become greedy. But it's actually very straightforward to ensure this, and maybe the simplest way to do that is just to use epsilon greedy exploration, and you just reduce epsilon at a rate like 1 over k, where k is the number of episodes. And if you do that, then both of these properties are met. That you're reducing epsilon, but your epsilon's still non-zero, so you continue to explore everything. And in the limit, as k approaches infinity, we're not going to explore at all. And so we really do become completely greedy. So if we do these two things, then it turns out that we can do some very, very nice algorithms that would just work. So we're going to use that greedy in the limit with infinite exploration, GLI idea, to do Monte Carlo control. So the idea is that we're going to, at the kth episode, so this is something we're going to run this update every single episode. So we're going to basically use our current policy pi to run an episode. So we're going to basically, so we have a policy, we're going to follow that policy for one episode, we're going to wander around our maze and pick up some experience, so we're going to see some states, actions, rewards until this episode finishes, sample that according to our current policy. And then what we're going to do is that for each state and action in the episode, we're just going to do our standard Monte Carlo evaluation. So this is just counting. We're just counting the number of times we visited state S and action A. And this is just that incremental update of the mean, where this is the return we saw following that state and action. And this is the error that we saw. So this is just an incremental mean update like we saw in the previous lecture. And now all we're going to do is improve our policy. So this was the policy evaluation part, and this is the policy improvement part. And so all we're going to do is reduce epsilon a little bit to make sure we're GLIE. And we're going to set our policy to be epsilon greedy with respect to our latest Q values here. So that's the algorithm. So does it work? Well, it turns out that this very, very simple idea actually finds the optimal action value function. So you run this very simple idea, and if you run it for long enough, you're guaranteed to solve your MVP perfectly. So even though we're just doing on-policy control, no one's told us the MVP. So this is our first algorithm that really does sort of solve the MVP completely, without in a model-free way. Okay, so back to Blackjack. So I promised we'd return to the Blackjack last time. So I thought I'd put up a slide to actually show it, because not everyone knew it. So this is the game of Blackjack, and this is the dealer with his card showing. There's one card that you can't see, sorry, it's not very good there. You just get to see one of his cards, and then everyone's sort of accumulating their cards. So this guy's got 10, 7, 20 so far, and now he can ask to stick or twist to get another card, and if he's got 20, he should probably stick there, because otherwise he's going to go over 21 and lose the game. So now we're going to use this GLIE Monte Carlo control algorithm to actually work out the optimal policy. So this is something you can just take this, you can go into a casino, and you can now use this strategy because you know how to do GLIE Monte Carlo control, and you'll probably still lose because they have they probably make sure that the tables are tilted in their favour somehow. But anyway, so this is now the optimal value function. So you can see here again, this is what the dealer's card is. So if the dealer has an ace, then you're in trouble and your value is going to be quite low. Dealer's showing something intermediate, you've got more chance. If he's got a 10, again, you're probably less likely to win. And this is your sum now. So if you've already got 21, there's a very good chance you're going to win. And this is how the value function drops off depending on what you have. And this is whether you've got an ace that you can use or you haven't got an ace you can use in the total. And now this is the optimal policy corresponding to that. So this is like the final cycle of our iteration. Once we've iterated all the way through, backwards and forwards, I think this was for 10,000 episodes, and then you reach this point where you've now figured out that the optimal policy is to stick or to hit. And you can see that after 10,000 episodes, you end up with this very smooth estimate of the value function. In practice, the algorithm is actually using Q star. It's just harder to illustrate that here. So this is the strategy to use, that when you should ask for another card and when you should keep the cards you've got. Okay. So any questions about sort of Monte Carlo control and this idea of generalized policy iteration? Is it making some sense? Okay. Good. So we're going to move on to temporal difference learning methods. So you remember from the last lecture that there's several potential advantages of temporal difference learning over Monte Carlo learning. It's lower variance. It's something we can do online. We don't need to wait all the way until the end of the episode. We can just update all the way through. And we can run it on incomplete sequences. So we can also use it in continuing environments where there's just some agent going round and round and round, and it never reaches the end of its sequence. Okay, so these are all significant advantages. So can we generalize this temporal difference learning, can we use temporal difference learning in the same way that we use Monte Carlo learning to make a control method? So the obvious thing to do is to just drop it into our control loop where we were using Monte Carlo evaluation. We're now going to use TD to estimate our action value functions. And again, we'll use epsilon greedy policy improvement. Now, one slight difference is because TD is something online, we want this online property. Now we've got something that we can do every single time step. So instead of waiting until the end of an episode before we update our value function, TD, we can update our value function after just one step. And so that means that we can make a tighter loop of policy improvement. We'll see that in just a second. So the basic idea is this algorithm called Salsa. And it's called Salsa because you start in some state and take some action, SA. You see some reward, R. You end up in some successor state, S prime. And then you take some action from your successor state, A prime. So that gives us Salsa. So it's the Salsa algorithm. And the update looks just like this, which is that we're basically going to do something to look just like our TD update we had in the last lecture, but using the action value function Q instead of the state value function V. And so if you look at this, what we're basically saying is the value of starting in state S and action A, we're going to do like this one-step sample. We're going to just take an action, see where we end up, and take an action from there. And we're basically going to back up from here to here. So we're going to back up the value that we ended up in. We're going to use that as a target and move the value here a little bit towards this value here. So that's what this is saying. We're going to move a little bit. We're going to move our Q value a little bit in the direction of the reward we got plus the action value of where we ended up. So that's the error between our target, reward plus this thing, minus where we started. So we're just moving incrementally a little bit towards the value of this guy here. So that's the Salsa update. And what we're going to do is use Salsa now as our policy evaluation algorithm in our loop. So we're doing exactly this is exactly the same diagram we just had for Monte Carlo control, except that we've now dropped in Salsa instead of Monte Carlo evaluation. We're basically going to use this update repeatedly. And the other thing is that we're going to update every single time step. So every single time step, this agent's going to take a step in the world. It's going to start in some state and action. It's going to take, it's going to see some reward. It's going to end up in some new state. It's going to see some new action, and immediately it's going to basically apply this update here. After every single time step, as soon as we get to our S prime and A prime, we're able to update where we were before. And so we've immediately got a slight change, a very small change to our queue. We haven't updated the states and actions everywhere. We've just updated one state and one action. But that's enough to change our policy a little bit. So we'll probably change our policy for that state and action we were in, or maybe we'll keep it the same. And so we're going to go around this every single step. We're going to go around this policy evaluation and policy improvement cycle, like this. And again, we're sort of hoping that we're really going to get to the optimal value and the optimal policy. So this is just the algorithm, so written out in pseudocode. So you start off with any action value function you want, and then each episode you initialize your state at the start of your episode. This is the episodic version. You choose an action using your epsilon greedy policy, and then you take an action, you see what happens, you update your action value function, move on to the next state and the next action, and then you just go round and round until the end of the episode. So what does this do? Well, the nice theory tells us that this actually works. So basically we need some one additional condition to what we had before. So basically all we need to know is that, so Salsa really does converge on the optimal value function, and we just need two conditions for that to be true. So we need our policies to be GLI-E, so we basically need exactly the same properties for our policies as before. So for example, epsilon greedy with the epsilon decaying down to 0. And we also need just that our step sizes, these alphas that we're using here in the updates, these need to also essentially decay down to 0 at the right rate. For those of you who are familiar with stochastic approximation theory, these are like the standard conditions that you need for any stochastic approximation. You basically, this condition just tells you your step sizes can take you arbitrarily far. If you add up all your step sizes, you can get wherever you need to get. So you need to be able to move arbitrarily far in your value space. And this tells you that your step sizes basically become small enough that you end up with no noise in the limit. You really do converge on something. So that's the second condition, that the squares of the step sizes converge to something. Okay, so let's have an example. So this is called the windy grid world. We've got another grid world example. There's this wind pushing upwards, and each action that the agent takes, if it wants to say go here, from here to here, it will then be pushed up in this column the number of cells that are marked in this down here. So if it takes an action from here to here, it will end up being pushed up 1. If it takes an action from here to here, it will be pushed up 2. And so it's allowed to move either northeast, southwest, or also diagonally. And it's going to get -1 per time step until it gets to this goal. And the question is, can we use Salsa to solve this problem? And the answer is yes. If you run Salsa for this number of time steps, so it's not a large number of time steps, this is the total number of time steps. So each episode to begin with might take quite a large number of steps before it stumbles on the goal. But then over time, after a few thousand time steps, it's found roughly the optimal policy. The reason this is still jittering here. So basically, what's going on here is we're looking at the number of time steps it's run for and the number of episodes it's completed. So to begin with, it takes it, maybe like 1,000 time steps to even solve the first episode, because it starts off just randomly doing a random walk. And then it takes less and less time until it's solving this gradient here is basically the optimal path here. And the jitter corresponds to the fact that we haven't yet decayed epsilon down to 0, so it's still doing some random exploration. So there's some variation on the length of these episodes. Okay. So any questions about Salsa control, about using TD for control? Okay. I'm going to move on to Salsa lambda then. So last lecture, at the end of last lecture, we saw how we can sort of get this spectrum between TD learning and Monte Carlo learning that we called TD lambda. We introduced this lambda parameter, which is this weighting function that combines together the different returns. So we actually defined this thing called the lambda return. So we started off with the forward view, and then which was sort of gave us the theory, and then we came up with the mechanistic view based on eligibility traces, the backward view. So we're going to start with the forward view. And so last time we saw this idea of the lambda return, where we're basically looking at the one-step return, the two-step return, the three-step return, and we're averaging all those things together using this particular geometric weighting based on parameter lambda. And we're going to do the same thing again here with Salsa, except that now our returns are all about action values now. So we're going to basically end up with the action value at the end of this thing here. So we're going to have the same weighting function, and we're going to combine together our returns. And the only difference with these returns now, these m-step returns, is we're using Q instead of V at the end to evaluate. These are states and actions. These black dots represent actions, and these white circles represent states. So we're going to start in some state and action, and we want to know if I follow one state and end up in some action, and then use the action value there, that would be a one-step estimate. This is our Salsa estimate that we just saw. You can equally look 2 steps ahead, and then use the action value estimate after 2 steps, the Q value after 2 steps. Or if you look 3 steps ahead, use the Q value after 3 steps. And we're going to weight those just the way we weighted them before, and now we're going to use this to generate an algorithm. So we're going to update our action values for each state and action a little bit in the direction of this lambda return. So we're weighting together all of these things with this geometric weighting where at each step we decay by lambda and by lambda again. So just as in TD lambda, we have a forward view and an equivalent backward view. And just like TD lambda, it turns out that the forward and backward views can be shown to be equivalent if you use offline updates. So what we're going to do is use eligibility traces to make. So again, the problem with this forward view is that in order to compute this lambda return, you need to wait until the end of your episode. You have to sort of, it's called the forward view because you need to look into the future. To do this update, you already need to know what the value of all of your returns going all the way into the future would have been. So it's something you can only do by sort of looking forward into the future. So to run this online, so we want an online algorithm, so just like in the last lecture, we're going to use eligibility traces. And the only difference is that now we're going to keep an eligibility trace for states and actions. So we can have one eligibility trace for each state action pair. And then the idea is we start off this eligibility trace at 0, and each time we see a particular state and a particular action, we're going to increment this by 1. So this basically says each time we actually see this SA, increment it by 1, and for every time step decay by lambda, and the discount factor. So it's just like the eligibility trace we had last lecture, but we're doing it on every state action pair instead of every state. And now we're going to update our state action value function for every state in action. We're going to do it exactly the same way. So the algorithm looks just like what we had before. We update our action value function a little bit in the direction of the TD error. That's this Salsa error here, the difference between the one-step look ahead and what we thought before in terms of the action values. We're going to update our action values in proportion to this error and the eligibility trace. So this eligibility trace, what's it doing intuitively? This is the thing that's solving the credit assignment problem. So this is the thing that's saying, you know, I've been in a whole bunch of states and I've taken a whole bunch of actions in the past. And which of those states and actions are actually responsible for the fact that I'm making a bad prediction at this time step? So you make some prediction at this time step, and you say, okay, well, I thought my value function was going to be 100, and I actually ended up in a state where I now predict it's going to be minus 100. There's a big error in my prediction, so where did I go wrong? And you sort of use these eligibility traces to now say how much you should update all of the previous states and actions to make sure that you're correcting that error. So everything that you've seen, all the states you've been in, all the actions you've taken might be responsible for that error. And you sort of update them in proportion to their eligibility and how recently and how frequently you've seen those states and actions. So that's the idea of a Salsa lambda. So this is the algorithm. You basically start off with some action value function. And in every episode, we're just going to initialize these eligibility traces. We're going to start off in the start state and pick our first action. And then for every step of the episode, we're going to pick an action, see what we got, see some reward and some next state. And then wherever we ended up, we're going to choose our next action using our, say, epsilon greedy policy based on our current Q values. So we're going to pick our next action using our epsilon greedy policy. We're going to calculate this TD error. So this is our, just like in our Salsa update, we're looking at one step ahead, we're going to look at the action value function. So this is the error between this thing here. It's the error between, it's this term here we're looking at. It's the error between what we thought the value was going to be from this action and where we ended up. So the action value from this action we ended up taking. So the error between this and this. So we're going to compute that error. Now we're going to update all our eligibility traces. So update the eligibility trace of the state and action that we're actually in. So if we're in state S and took action A, this is the eligibility that then gets increased. This guy is something we've now seen. We want to increase this one. And then for all state action pairs, we're going to update the action value function in proportion to this TD error and the eligibility trace. And for all state action pairs, we're going to decay their eligibility trace a little bit. Okay, so that's the Salsa lambda algorithm. So I put up pseudocode for some of these actual control algorithms. I think it's quite useful to see them actually turned into algorithms. And I'm going to talk a little bit about the assignment in a minute as well. You'll need to know some of the algorithms. Okay, so why is Salsa lambda useful? So this plot here kind of is here to give you some just intuition into what happens with this Salsa lambda, where you have different values of lambda for updating your Q values. So we've just got some grid world, and the agent's sort of done some random walk or followed some policy to get to this goal here. And to begin with, let's say it's behaving randomly and all its action values are 0. And then eventually it gets to this reward. Let's say all the rewards along the way, in this case, let's say were 0 as well, until it gets some positive reward at the end. That's what's happening in this example. It's got 0 reward, 0 reward, 0 reward, and then at the end it gets some positive reward. So if we just use TD learning, like TD0, and ran that in our Salsa algorithm, so if we wanted to update our action values, and we used this one-step update, Salsa 0, the Salsa algorithm we started with, then what would the updates be? Well, we started off thinking if we went east from here, that we would end up, so we had a prediction that our value function was 0 if we went east from here, and we ended up in a state where the value function was 0. And we got 0 reward along the way. So the error is 0 here. We started off thinking we were going to get 0 reward, and we ended up getting 0 reward for just that one step. But this next step, the same is true. We started off predicting 0, we ended up in prediction of 0. And all the way around here, all the way along the path, the predictions are just, there's nothing to do, there's no change. Until the very final step. The very final step, we were in a place, we predicted that if we went north, we would have a value of 0, but we ended up in a situation where we did get some positive reward. So we're actually going to have a positive update here now. So we're going to update the action value function of that particular action from this particular state towards the reward that we see. And if we were to run another episode, and we were to end up, say, moving into this state, in that next episode, we would then see some error on this transition, because we started off predicting 0 from here, and then we ended up with something with a non-zero prediction here. So there would have been an error there. And slowly, all this information would propagate back, all the way back to the beginning of the trajectory. But you'd need a lot of episodes in order to actually propagate that information all the way back to the beginning of your path and find the optimal path. In contrast, what happens when we use Salsa lambda? When we use Salsa lambda, what happens is we run this one path, we run this one episode, we end up getting there, and we've got some eligibility trace that basically remembers that we've passed through all of these states and actions all the way to here. So each of them has accumulated some amount of eligibility, and the amount of eligibility that we've accumulated just sort of mounts up and mounts up because these are the most recent guys. And what's going to happen then is that when we actually see this error at the end, so finally we see an error, and we say, well, who's responsible for that error? And the algorithm says, well, all of these ones here are responsible, but in varying amounts. It starts off saying this one's probably the most responsible, then this one, then this one, then this one. So they all get updated a little bit in the direction of the error and in proportion to their eligibility trace. And so they all get increased slightly, these action value functions, all the way along this trajectory. So we ended up getting some positive reward where we predicted 0 reward, so now we're going to think that all of these guys should have had a slightly higher value function. And you can see that much more rapidly this is going to accumulate, this is going to find the optimal solution. By the way, it's probably worth adding that the TD solution is actually quite, there's other ways to fix that as well, one of which is just to run your episode in reverse. If you just ran your updates in the reverse direction, that information would propagate all the way back in one episode. That's kind of a detail. The point is that when you're running online, the only way to get this propagation of information is by keeping eligibility traces. And the extreme case where lambda is 1 is equivalent to Monte Carlo, remember? So everyone would take equal credit, and that's just like updating the means of all of these guys a little bit towards what you saw, with equal credit. Okay. So, any questions so far? Right. Off policy then. So now we're going to move on to this next idea. We want to learn about some target policy pi, whilst we're following some behavior policy mu. This is looking over someone's shoulder. So can anyone think why this might be important? I've got a few answers, but just why might you care about this problem? Why might it be a worthwhile problem to look at?
You can let somebody else expect.
Yeah. Yeah, that's a really good point. That someone else, you might be in some dangerous environment, and it really costs a lot to have some negative reward. So if there's just, maybe it's a multiple agent scenario, and one agent falls over, and 100 agents are able to learn from that, not to make the same mistake.
Can you run paths concurrently in parallel and have them learn?
Yeah. So So another way to put that, well, let me run through some of the reasons I think it's important, and one of them is similar to that. So the first point is similar to yours, that we might want to learn from observing other agents for the reasons that you don't want to go through all that learning cost yourself and the hits of taking the negative rewards and so forth. You might want some machine to learn from human behaviour. The natural way to do that is you just you let it learn off policy. The human executes experience, and the agent learns off policy just by observing the human. There are also scenarios where this is the only possible way to do it. That it's just not possible to run your agent. For example, there's some maybe there's some data out there. Maybe you've got some data from some sports. You've been watching football games and you want to know what's the optimal way to play football. You've got the data of how humans play football, and you're just interested in, well, was there a better strategy? You can look at the data, you can run your off-policy algorithm, but it's not possible to run your algorithm and actually put artificial football players out there and run games and really learn what would happen. It's also, you can use it to reuse experience from old policies. So we go through this whole sequence of policies in our algorithms where we've been improving our policy, improving it again. And so far we've just sort of thrown away the old experience once we've used it and just used it to generate our new policy. But you might want to sort of go over and over those old episodes and get a more data efficient algorithm that was able to use its old experience. But the problem is that old experience was generated from a policy that's different to the one you're trying to learn about now. So you need to be able to, if you want to do that, if you want to go over your old experience again, you need to be able to do it off policy. You want to learn about your current policy from experience generated by old policies. Probably the most common reason that people actually use these off-policy algorithms is the following one. That you might want to learn about optimal behavior whilst following an exploratory behavior policy. So it might be that you really, you want to explore a lot to figure out what happens if you go to all these different parts of the state space. But at the same time, you don't care about what happens whilst you're exploring. You care about what happens, what's the best you could possibly do. So in that case, the target policy might be the optimal policy, and the behavior policy might be something which does a lot of random actions, which just helps you visit the state space very effectively. And finally, which is I think closest to your point, you might want to have something where, well, maybe it's slightly different, but this is sort of, imagine that you might imagine there's just one policy that some agent is following, but it might want to reason about all kinds of different behaviors that it could follow. Like I might be walking out of here downstairs, but I'm at the same time, from that experience, trying to figure out, well, what if there'd been a fire? What would I have done? Would I have run out of the building? Would I have gone a different way? And I don't want to have to wait until there's actually a fire to evaluate that policy. I can think it through just from my experience of running one different behavior. And the idea is that, one theory for how the mind works is that there are sort of thousands and thousands of candidate policies being contemplated simultaneously. The brain is sort of learning about many, many different behaviors that it might execute whilst it's just following one real behavior. And if it can learn about all those different ways to behave whilst following just one behavior, then we've got a very rich representation of our world in our minds. So those are just some reasons why you might be interested in off-policy learning. There are sort of two main ideas of how to do off-policy learning. The first is based on this idea of importance sampling. So importance sampling is a sort of well-known tool, and the basic idea is to change the distribution to which we're taking an expectation. And the trick sort of goes like the following: that let's say we want to compute some expectation of some function f of x, and x is drawn from some distribution p, but we want to know about some other expectation. We want to know the expectation of f of x with respect to some other distribution q. Well, what can we do? Well, we can do importance sampling. And the idea is we just write out our expectation, and then we multiply and divide by our distribution q. And now you can see that this is something that's actually an expectation over q, but multiplied by what we call these importance sampling ratios here, these p over q ratios. And so we've got an expectation with respect to these importance sampling ratios of the functions we care about here. So we can sort of rewrite any expectation with respect to a different distribution as long as we take account of it by incorporating these importance sampling ratios. So in reinforcement learning, most of our algorithms have been trying to estimate expectations. We've been trying to estimate value functions, which are expected returns. So can we use the same idea to estimate expected returns? Well, let's do that with Monte Carlo learning first of all. And the idea is to use the returns generated from our behavior policy to evaluate our target policy. And so what we're going to do is basically, we're going to get the returns from following our behavior policy, but we're going to weight those returns now by basically saying how similar was the behavior policy to the target policy along that particular episode. And if they behaved exactly the same way all the way along, well then we can take full account of that return. But if they're very different, we should essentially ignore that return. And so the way to do that is just to multiply the importance sampling corrections along every single step of the episode that we saw. So we're going to basically, this is our sort of weighted return now, and we're just going to take our importance sampling corrections, the ratio of what the two policies would have done. So the ratio between policy we care about and the behavior policy at every step along the way. And so if these ratios are very different, we can end up with very extreme values here. But on average, because of this importance sampling property we saw, when we average over these things, if we move towards this thing, then in the mean, we've basically corrected our distribution towards the real distribution. We're sort of dividing out the behavior that we were using and multiplying by the behavior we care about instead. Sort of the way to think about it. And so all we do is we take our algorithms that we had before. So these were our Monte Carlo evaluation for state action or for action value Monte Carlo evaluation. And we just replace the return that we had with this sort of corrected return here. Now, it's a good idea. So one problem is that this only works if there's some similarity between our policies. So in particular, you can't use this if you want to learn about some policy that your behavior policy you want to learn about something that you want to learn about some target policy and your behavior policy just never ever does it. So you want to learn what happens following some action and this behavior policy just never takes that action. It's impossible. And the bigger problem is that importance sampling dramatically increases variance. So you can see that these ratios can be extremely large or extremely small based on these ratios between your policies. And if your policies are very different, you can get these very extreme values, and we're multiplying these extreme values together over all the steps of the episode. And so these things can become either enormous or vanishingly small. And that means that in practice, this algorithm isn't great. It's nice in theory, but it doesn't work in practice very well. But it's good to know about. What does work better is when we move to the TD case. So I'm not going to do this for control just yet, that'll be the next slide. But just for to do off-policy TD evaluation, so now our policy again has been generated, I think this is the wrong way around. This mu is the behavior policy, we want to evaluate pi. And we're going to basically come up with our TD target, just like in TD learning. We're going to look one step ahead, we're going to see one reward, and we're going to look at the value function one step after that. But now we just need to weight this by what happens over that one step. We don't need to weight all the way through the trajectory. We're just looking one step ahead, so we only need one single importance sampling correction. So we're basically looking one step ahead. We're going to update, this is our TD rule, we're updating our value function a little bit in the direction of the TD error, but all we're doing is we're correcting this by one importance sampling step here. So our target is just slightly different. So this basically says, we're very different, we're going to modify this correction slightly. And this is much lower variance than the Monte Carlo, for example. Okay, so this actually works in practice. And some people do this, but the most popular algorithm for off-policy learning is the following algorithm. This is probably one of the best known algorithms in reinforcement learning. It's called QLearning. It was invented by Chris Watkins, who often visits, he's in London, often visits UCL. And the idea is to learn about the optimal policy, pi star, and experience sample from the behavior policy. So basically, we want to figure out our Q star. We're going to estimate our Q from that. The difficulty is that the behaviour policy itself, when we're doing this sort of cycle of policy improvement, the behaviour policy itself depends on our current estimate. So if we're doing something like epsilon greedy, then our policy actually depends on, the behaviour policy could depend on what we're doing if we were doing something like epsilon greedy. And so the idea of this algorithm is that even if we're using something like epsilon greedy, the behaviour policy is changing. It's not, so now we don't have a fixed behaviour policy. We've got a behaviour policy that's something like epsilon greedy, which is going through this whole sequence of improvements. But while that's happening, we're sort of trying to learn about the optimal policy. So we're sort of watching this sequence of improving policies, and we're trying to learn about the optimal policy. And the advantage of doing this is that our behaviour policy sort of gets closer and closer and closer to the thing that we care about learning about, which is the optimal policy. So unlike the previous case where you can have these like big divergence between what you're trying to learn about and what you're actually doing, here it gets closer and closer. So this is the algorithm. So it's a bit compact, but the basic idea is that there's a maximization step now. So the idea is we're doing a one-step look ahead again. So we start off with our action value function Q. I'm going to move our action value function a little bit in the direction of the following error. So we're going to look one step ahead, and we're going to say, okay, well, if we were acting optimally from this step here, we'd be able to maximize over all the actions that we could take at the next step. That's what this arc here represents. This is basically saying you start in state S and take action A, you get some reward, you end up in some new state S prime, and from that new state S prime, there are all these actions A prime you could take. There should be a prime there, I like A prime. And we're going to maximize over those actions A prime, and we're going to look at the difference between the maximum of all those successor state actions that we can take and what we thought the value was. So the maximum value of all these guys compared to our prediction of what we were going to do. So we get to choose which of those actions we're going to do next. So if we care about the optimal policy, we can always do this. We can always say, when we get to this state, we get the chance to maximize. So we're updating the value function here towards the maximum successor value here. And so that's this error here. It's the QLearning algorithm. And the algorithm is very, very simple. It's very straightforward. We basically start off with some action value function, and then for each step of this episode, we're going to pick an action from our epsilon greedy policy. We're going to take that action, we're going to see some reward, some new state, and now what we're going to do is we're going to choose the next action by maximizing. So whereas before in Salsa we were just picking it according to our actual policy, our epsilon greedy policy, here we're considering what would happen if we actually maximized that action value function. What would happen if we took the best successor action? And we're going to update our value function towards the best successor action, the value of the best successor action. So we want to know, what should we update the value here towards? Or we should update it towards the best action value that we can choose at the next step. Yeah?
Just a quick little point. Should there be brackets around the max Q minus Q?
No. So the bracket should be here. So
it should. Okay.
So this term, the maximization is only over this.
But I mean, as in the gamma, when you multiply it by the gamma, are you multiplying just the max term by the gamma, or you multiply the difference between the two by the gamma?
Just this.
Just that.
So this max is, so the way to read this is that the max is Q here.
No, I mean, you multiply by the gamma, you multiply the max by the gamma.
Yeah, so it's gamma times the maximization over Q S prime A prime, and the gamma is not multiplying this time.
Okay.
We just want to, so I mean intuitively what's happening is we're starting with some estimate up here. We want to look at the error between what we estimated and the reward plus the discounted best action that we could take from the next step. So the reward plus the discounted next action we could take. We're looking at the difference between that and our start action value, which is not discounted. Okay. So, so you might have seen me faffing around at the beginning of the class. That's because I was, for some reason, not able to get this demo working on this machine. I'm not sure why. I'll try again in a minute, but if I can't, I'm just going to carry on. So sorry about that. What I'll show you instead is as an example, just to give some intuition. What I might do is, if I can't get this working, what I'll do is I'll just send around a URL, put it up on the website, And you can look at this demo, it's just online. It's the follow-up of the demo I showed for the value iteration of the previous class. But here's something to give you some intuition about the difference between like QLearning and Salsa. So Salsa was our on-policy model-free reinforcement learning algorithm. QLearning was our off-policy algorithm. Now here's a sort of a little toy grid world that sort of helps understand intuitively the difference between these things. So we call it the cliff, and the idea is that you start in this state S and you're trying to get to this state G. And there's this cliff along the way where if you walk off, so you get a reward of -1 every single step you take to get to G. But if you walk off the cliff at any single time step, you're going to get this massive negative reward of -100. Okay? So then what's the right path to take? What's the optimal path? And it depends on your definition of optimal. So let's say you really want to find the optimal policy. Well, the optimal policy is clearly to sort of hug the cliff and go all the way to the goal. Yeah. But if you know that you're exploring along the way, like Salsa is exploring along the way, and if you want to know, well, given that I'm exploring along the way, what's the best thing to do, then you shouldn't hug the cliff because you know that you're going to explore sometimes, and if you're exploring sometimes, you're going to fall off the cliff. So Salsa will choose to go far away from the cliff to make sure it never ever falls off that cliff and moves all the way down to the bottom here, like that. Now, that sort of gives you some intuition as to what's going on with them. So, you know, what's the right thing to do? Well, it all depends on your problem setup. So sometimes either of these can be appropriate. You don't always have cliffs. But the key differences are, you know, whether you care about what happens while you're exploring. Are you learning online about what happens when you're actually exploring? Or do you just care, essentially you're trying to figure out something that you might apply later. Maybe you've got some kind of offline setup, you just care about observing some data, and you just want to know really what's the optimal policy in this situation if I was able to turn off exploration and then run it, which is the QLearning case there. Okay. So I'd really like people to try and understand this slide. If you understand this slide, then you've sort of got it in some sense. You know, this is kind of the summary of pretty much, you know, the first half of this course in one slide. So if you get this, then you're doing really well. And the basic idea is I'm trying to show here the relationship between dynamic programming algorithms from the previous lectures and the TD algorithms. And what we see here is, again, we saw this in the dynamic programming lecture, but there's two different Bellman expectation equations. We might care about the Bellman expectation equation, or the Bellman optimality equation here. And if we're just doing policy evaluation, then we can use this expectation here to do iterative policy evaluation. That's the full width version where we do a full backup. Or we can just take one sample of this diagram. So we sample an action using our policy, and then we sample the dynamics of the environment. We just sample what happens to us, and we find out that we're here. And so we just learn from that one single sample, and that's TD learning. We can turn this into a control algorithm in one of two ways. We can continue using the Bellman expectation equation, and then we can turn this update here, we can turn this, we can basically use our cycle, our generalized policy iteration. So we can do exactly the same as before, but using action value functions instead of state value functions. So you start off with your Q values for some particular action. You can do a full look ahead to the Q values of the successor states. And in the dynamic programming lecture, we called that Q policy iteration. And if we do that by just taking one sample, so the sample-based version of this is Salsa, where we just sample one particular action, we end up in some particular state, and we sample our policy to take our next action. That's Salsa. Now, what we saw in the last section of this class is that we can also do something equivalent to the optimality equation. So this was equivalent to value iteration. So we did control using value iteration in the dynamic programming. So you could do that using the Q values again as well, where you basically do a full look ahead of, so you start with some action, you can do a full look ahead of all the things that the environment might push you into, and then a full look ahead of all the best actions that you might take. This is like a maximization over all the actions we could take from that state. So this was Q value iteration. And if we just sample this, if we take one sample down this trajectories, we end up getting our QLearning update. Where we're just taking one sample and we're looking at one sample of this Bellman optimality equation. So another way to say that is that basically the dynamic programming updates are equivalent to the TD updates that we've looked at, TD learning, Salsa, and QLearning, but in expectation. So these things are really doing full expectation of what's going to happen to you, whereas the TD algorithms are just taking a single sample. So if we look at TD learning, for example, we're taking a little step, this alpha step, towards R plus gamma V. Whereas in dynamic programming, we move all the way to the full expectation of R plus gamma V. So this expectation is this full consideration of everything the environment might do to us. And similarly for Q policy iteration, we get to Salsa. We just have this full expectation over everything the environment might do to us. Whereas here we're just taking one sample and moving just a little bit in the direction of R plus gamma Q. And similarly, Q value iteration is the expectation version of QLearning. So in expectation, QLearning is doing the same as this dynamic programming version of value iteration. Okay, so that's sort of the summary of all of these things put together. So just before we finish today, there's a couple of admin things I wanted to do. So I've been contacted by a representative of the MSc students saying that there have been some requests to start earlier and finish earlier to be able to get to the next class. But I know that's not what everyone wants, because I know some people also don't like starting classes earlier. So I just wanted to have like a referendum in that I will only change it if the majority of people in the class would prefer a change. So can we just get a show of hands about whether to move the time back from 9:30 to 9:15? So we move it back by 15 minutes, start and finish 15 minutes earlier. So this was the request. So we just have a quick show of hands for those in favour of changing the time. Raise your hands. Okay, there must be some people. This was being raised. Those against changing the time, raise your hands. Okay, that's pretty comprehensive. Okay, one other piece of admin. So the assignment. I will be putting the assignment up today. So if you check my website later on today, the assignment will be up. Very, very briefly, the details will be up on my website, but very briefly, the RL assignment will take the following form. The idea is that I'm going to give you a very straightforward grid world MDP. It's basically going to be a grid with randomly placed obstacles. There's going to be some grid world index from 1 to n in both x and y. And in MATLAB, you can basically, this is all, you don't need to write this down, it's all going to be on the assignment. But it's going to be very straightforward to generate these obstacles for yourself in MATLAB just by using this pseudo-random number generator. And if there's a 1 there, there's going to be an obstacle. We're going to generate this binary grid, and where the 1s are is where there's an obstacle. There's going to be a discount factor, and the idea is that you can move this around this grid world, north, east, south, or west, with some transitions. And what I just wanted to explain briefly is how this is going to work. Where when you take actions in this grid world, you get to move in the direction that's intended for probability 0.5. It's going to be a random MDP, so stochastic transitions. So if you try to go north, with 0.5 probability you'll go north. If you don't go north, then there's a chance that you'll either slip north, east, south, or west with probability 0.5. And if you don't do that, then there's a probability that you'll jump to any cell on the whole grid with probability 0.1 over n squared. So if there's a grid of 10 by 10, then this would be 0.1 divided by 100 for each of those cells. So 0.1 in total, probability in total. And if as a result of any of these actions, you would end up either going off the grid or landing on an obstacle, then the agent just stays where it is instead. So that's the dynamics of the MDP. And so the assignment, and there's rewards for +1 if you reach a corner, and -1 for every other action. And the assignment is basically going to be to implement this MDP in 2 ways. The only thing I really want to just emphasize, I know we're running out of time, is I want you to do this in 2 ways. First of all, to make it as if we're doing the MDP as known, and then we're going to do it as if the MDP was unknown. Okay, so we're going to do both planning and reinforcement learning using the same setup. So first of all, if the MDP is known, well, I want you to actually compute the MDP, work out the transition matrix and the reward vector, and then you'll do some planning with this. And the second way is as if it's unknown. And what I really want you to do there is sort of, even though you've just computed it, you now need to sort of pretend that you don't know it. And what you need to do is implement this step function. So all you're going to have is just something as if, which tells you, if I was to take this action from state S, and I was going to take action A, then what reward would I get, and which state would I end up in? Okay. And then the assignment is basically to implement a bunch of planning algorithms in the first part, and then reinforcement learning algorithms for the second part. And I won't go into the details now because we don't have time. But what I do want to say is what I'd like you to do, which is just to email me by this date a PDF with all your plots and results corresponding to the assignment, and a zip file containing all the source code. And I should say that last year there was unfortunately one person who submitted very late their assignment and did lose an awful lot of marks. And I just wanted to just remind you, we have to keep to the university guidelines for late submission. It's unfair on everyone else if we don't. And plagiarism is also taken seriously, so individual work is. Okay, so by the end of today, that will be on my website. Thank you, everyone.